Hi everybody. So I'm here today to talk to you about killing servers and how not to kill servers and how to use serverless instead. I'm going to particularly talk about scaling concurrency and try and explain how you can plan building your apps to take advantage of this wonderful scale of public cloud and function as a service, and also other technologies like databases as we go along. So a little bit about me first. I'm a technical developer evangelist at AWS. Like you said, I've been here exactly a year today. So I'm happy because my shares come through today. Woo! Drinks are on me. And my background is in operations engineering. I very quickly was doing DevOps before DevOps was a thing. I moved into architecture and doing cloud migrations as a consultant. And one of my first stories that I'm going to tell in a second is about when I worked in media. But we'll get to that in a second. So first of all, the obligatory slide we put at the beginning, the advantages of serverless. I animated this because I was so bored of doing this slide. We all know the advantage of serverless. There's no service to manage. If you're using a public cloud service, it's flexible, it scales effortlessly, it's highly available, and you don't pay for idle costs. I often talk about containers, which is kind of controversial in a serverless environment. And even with technologies such as Fargate, there's still wasted capacity. You're still running a container for 24/7, maybe multiple copies of them. You've still got wasted resource. Serverless is far more efficient and far more cost efficient for you as well. So my first slide's about BS. That's before serverless. I know what you're thinking, filthy minds. So I mentioned I used to work in media, and one of my favourite examples is the media scale of events. We used to call it, when I was over in the Channel 4 days, we used to call it the Davina McCall effect. She used to come on TV and say, go to channel4.com/1,000,000 drop, and bam, the traffic would arrive. And this next video is hopefully going to kind of show you what I mean by this. So we'll have this playing in the background. This is actually from 2012 and the One Born Every Minute episode. So what you'll see here is a program called Logstalgia. I've included the URL down here. And what's happening here is we've got a load of anonymized IP addresses. They're all making requests to my web server. Now, this is days before we had serverless. This is a monolith app. And there's actually some really bad practices going on in this website. There's some static content, JavaScript and images being served from the web server. Now, in this serverless world, you take advantage of things like object storage and take advantage of CDNs and actually distribute that load. You move away from it. You break in your code and your presentation layer up naturally because it naturally fits that one function, one job. Where am I going to put my images? S3, for example. So you get away from things like this. Now, this is background traffic whilst the show is going on. So this is people who are sat there with their iPads or with their Pixels, and they're sat there browsing One Born Every Minute as it goes on. Personally, I had to look after this site, and it was not a pretty site to look after. I've seen way too many births for my liking. And you can see the hit counter going up fairly modestly in the back here. Now, as we get along this video, I will then time sync it with a commercial break. And at the commercial break, we do this on-air call telling people to go to the website. And you'll see what starts to happen. Here we go. So this is a commercial break coming up now. We're actively promoting the website, on-call action, and that hits. Look what's happening over here now. Our server's going into meltdown. The traffic is jumping up at a rate. We've already doubled the amount we had in the first section of that video, and we've got a huge amount of traffic coming in. Now, the reliance of this being a server and a monolith, the scaling of this was incredibly difficult. As an ops engineer, I used to work with 50-plus agencies who all used to create websites for different shows. And we had to make those scale and work. And The quality of these agencies varied. It could be one man and his dog in Brighton, or it could be a great big agency up in Leeds giving us a really nicely rounded site. But we had the same issues from everybody. It was making these things scale, and nobody really got this, the amount of traffic that can come. I mean, we're now coming on for tenfold the initial amount of traffic. And scaling these things is difficult. So I've dealt with scale. I've felt the pain of scaling servers. And when I say as an ops engineer, if you don't have to run a server, don't run one, that's quite significant because most people go, operations, my job's going. It's not. It's changing. We're doing different things. So that's scale. It used to be TV companies. It's not anymore. Social media can do this to your website as well. You get a social media tweet from a big celebrity, they like one of your products, this can happen to you. And if you're running on traditional software stacks and server-based technology, you need to be able to deal and cope with this. Now, one of our secrets of doing this whole thing was we knew exactly when that call to action was going to go out on air. I could scale up beforehand. And why did I do it beforehand? Why didn't I rely on autoscale? Autoscale cannot respond quickly enough when it's bringing up virtual machines, even containers, I dare say. It's a very, very hard thing to bring up that much of resource that quickly. One of our sites, when we did the very first Stand Up to Cancer charity, we went from a 30K a second background traffic to 3 gigs a second traffic in 3 seconds. And that's a huge amount of traffic arriving at our site like that. So if you're going to do that on servers, get ready for some really, really hard work and some complex things that you just don't see at scale. However, what I'd recommend is, not playing the video again, what I'd recommend is let's think about the scale we have with things like serverless. And I'm going to start by talking about Lambda. So I'm going to talk about function as a service-ish Lambda stuff. So first thing you do when you see Lambda, you think, whoa, look at the size of that thing. I'll try and get film quotes in here, I'm sorry. And what we say is that you can do 1,000 concurrent executions at any one time in a region. Sounds massive. And it is, but it's not quite as clear-cut as that. So I'm going to dive deeper into some of those things as we go along. How do we calculate how many concurrent executions you can actually run? And is it really just 1,000? Can you go higher? So first of all, we have this function in our documentation. The number of events per second times the function duration equals concurrency. So it differs depending on whether you're doing a polling execution or you're doing a stream-based polling, or if it's just purely event-driven. So one of the things to look at, and I'm referring to my notes here because I always forget the numbers. If we look at S3, for example, S3 can publish 10 events per second. So actually my Lambda execution is now limited by how many events S3 is able to tell my Lambdas. So if I've got 10 S3 events per second and they run for 3 seconds, I can run 30 concurrent Lambdas a second. So you have to consider that. And it's all in bursts. Now this rate is going up and up at the moment, so that may be defunct data at the moment. Please don't quote me on that. But, this is improving as we go along. So you have to think about where your event-driven message is coming from and how's that going to affect your concurrency. So don't just think, wow, we can scale to 1,000 users at once or 1,000 executions at once. Not necessarily. You've got to consider these things as you go. And this is like a non-poll-based event that's happening. Now, if we look at poll-based and if we look at things like Kinesis or DynamoDB, the number of concurrent executions is going to be limited by the number of shards we've got in our database or on our stream that's come in. This is a streaming poll-based source. So, for example, if we've got 100 shards in our DynamoDB, when data changes in those shards, it will notify Lambda of a change, and Lambda can then go and do something with that data. If you've got 100 shards, you can have 100 concurrent executions. So that's how those figures kind of get pushed in. Right, it gets quite mind-blowing here, doesn't it? I've got another formula for you as well. So, poll-based, and this is the most complicated one. Poll-based event sources that are not stream-based. Try saying that after a few drinks. I've not been drinking yet. I'm just going to add that to it. Yet. So here I'm talking to things like SQS, where we've got a queue. We've got loads of messages landed in the queue, and SQS can now invoke Lambda functions. Well, what happens is our Lambda functions will poll that SQS queue. And we kind of have to walk a bit of a tightrope. We've got to balance that polling to make sure there's no messages in the queue with keeping cost low when your queue's empty. And then we have to be able to instantly scale that up to a massive scale when thousands of messages land in your queue. So if somebody's doing a voting app, for example, and loads of messages all arrive at the same time, we've got to be able to scale there. So what happens? So each batch message, so there might be more messages in an SQS come through, is a single unit of work, is a single concurrent execution. Now, what happens in the background? When there's an influx of messages, you initially start out with a burst capacity, depending on the region. So if we take one of the smaller regions, you start off with 500 concurrent executions that can happen. And then each minute will give you 500 more up until the limit in that region. So some regions, like Ireland, for example, you can go for 3,000 straight away. So most of us will never hit a concurrency issue like that. So what happens here is we first check, and we do that, and we batch 5 messages together, and we have 5 concurrent executions, and then we can start adding more and more as we go along. And that can happen 500 times. So 5 times 500, that's a lot of messages you can process in one hit. Now you can burst up to 3,000 in some regions, and one of the things we do, these 3,000 limits here, most regions are locked to 1,000 executions concurrently, but anybody, and this is a weird way of putting it, anybody in a good standing with their AWS account, that means you paid your bill on time for a few months, automatically gets a 3-fold increase. So that's why these regions will support 3,000 and not 1,000. So if you use Ireland, soon to be Frankfurt as well, we'll do 3,000, but also the 2 US zones, you can do 3,000 concurrent executions at any one time. So that's a huge amount of capacity. And I would have killed for this when I was doing media competitions and stuff like that in order to process incoming requests to try and win a prize. It would have been absolutely brilliant. Now, I'm going to give you a caveat here. It's not as easy as it seems. So one of the things I always say with Lambda is, a lot of people say, I want to make my Lambda functions super private. I'm going to put them in my VPC. Your VPC is your virtual private cloud. It's your own private networking space. Now, there's a couple of things that happen when you do this. Only do this if you've got a legacy system running in your VPC or on a VPN link into AWS. It's in your data center. Because all it gives you is a private network access to a resource that you already own. So it might be a legacy database, for example. Now, what happens when you create a Lambda and it gets connected to a VPC is the Lambda comes up, and then we have to attach an elastic network interface as well. That elastic network interface has to go and say, can I have an IP address? Gets an IP address. Once all those things are connected, the Lambda can execute. So you've got a little bit of a slower startup time. You're going to impact your speed of execution with Lambda. But also, you've got to think about your subnets that you're building within your network. So subnets is something that we all thought we don't have to think about anymore. But when you put Lambdas in VPCs, it does. If you've created a load of small subnets, let's say a /8, for example, /28, /8 is huge, a /28, you've got 14 usable hosts. So if you said your Lambda function can only run in one subnet, you could only ever run 14 concurrent versions of that function, because they all have to have an elastic network interface attached to it. So if you don't need to do anything that's connecting to legacy systems over private links, don't use Lambda functions in VPCs, just use Lambda functions as they are. And it's still the same execution plane that's doing it. All we're doing is attaching a network interface into your account. So how do you manage this concurrency? So let's have a quick look at this. And we said 1,000 executions per region. I've already said you get a threefold increase. But if you do need more, just open a support request. Say that you want to do that and you want more executions per second, and you'll be given an account raise quite quickly. So let's have a look at unreserved concurrency limits. So by default, per region, so you could do this all across the world and run thousands times 16,000 at a time if you used every region. We've got 1,000 we can use. Now, if my first two functions come along and they take up, say, 600 executions, they're taking up 300 executions each, and I've got 10 functions, the rest of my functions get squeezed, and they can only ever use the remaining 400 execution capacity. And that might be a good or bad thing. You might want this to be able to use up all the capacity. But if this goes along and uses up 9,999 executions, that means you've then got 9 other functions that can only execute one every second for the duration of the others. So you've got to think about, do you just want to use unreserved concurrency limits? Because you might hit a problem where one function is running away and using up all the resource within that region. So do think about that while you're doing it. So what could possibly go wrong with using unreserved capacity? Now, I'm going to show you an example on an architecture diagram here, and please don't judge me on it, because I would say never build an application like this. But we're going to start off with a relational database, and it's because it's got legacy data in. That's the narrative I'm going with here. So in here we have a voting app on a phone. We've decided we're going to rewrite the monolith we had before, and we're going to replace it with Lambda functions. So we come into API gateway, we say we're registering a vote, we go to function 1, and then we move off and we push that into our relational database, and it gets written. And then when we want to see what the score is, we also come to this and we say, can we see what the voting currently is? And we go and read the database and we get the data back and we display it nicely to the end user. And then any static assets we've now moved over to S3. Now, it'll probably work to a certain degree, but when you start getting to that media scale event that I showed you there, you're going to hit problems. Anybody who's ever done any architecture and engineered anything out and improved the front end so much knows that the very next thing to break is your database. You're going to put pressure on your database. If you can handle all this capacity at the front end, the database has got to keep up with it. Now, there are a few tips and tricks to go with that, but if you don't do anything, you're going to end up with something like this. Oops, my MySQL server's gone away. And you're not going to be able to write to it. If you get 1,000 concurrent executions a second, all trying to write to a database, a single database, you're probably going to overwhelm it pretty quickly, and you're probably going to knock it over, and your website's going to go down. So there are a few things you could do. You could start putting read replicas in there. So you could drop some read replicas in, and when people are requesting to see what the current state of voting is, they hit the read replica, take some pressure off the master, and therefore kind of relieve a little bit of pressure, but you still might end up with a problem. You could go one step further and stick in some caching like Redis or Memcache. Yeah, again, you're not really solving the problem, you're masking it in layers of caching and read replicas. And the big thing about this is it's starting to get expensive. Instead of now having one database server I've got a bunch of read replicas. I might have another master. I might be doing cyclic replication on masters. I might have a caching server. I'm not going to have one caching server. I want high availability, so I'm going to have a cluster. This is going to start getting expensive. And the whole idea about using serverless is to get rid of idle costs and servers to manage. And now you've got a load of servers to manage. You've got to think about your backup strategy. You've got to think about what do you do when one of those read replicas starts lagging? How do you detect that? How do you move away from those problems? You've given yourself a load of operational overhead that you're trying to get away from by using serverless technologies. So try and avoid doing things like that. Instead, let's go for something much, much nicer. Let's switch our database over to DynamoDB. DynamoDB is a NoSQL database. It scales pretty effortlessly. You just tell us how many read and write capacity shards you want. You can now take advantage of auto-scaling there as well. And what we're doing here, instead of always everybody asking the database for information, we do all the writing to the database, but on a data change, we can trigger another Lambda function, and we can update a static asset that lives in S3 that's got the current scores, the current voting scores in there. So we're moving everything to that proper event-driven process. We're not relying on relational databases and manipulating data and churning loads about and having loads of connections that may time out because you've run out of connections to your database pool. So look at doing things like that. The limiting your app is the next way to look at this. So that's moving to a better architecture there, using event-driven based. But still, you might want to control things like costs. You might not want to have 100 shards for read-write capacity on there. You might want to have a fairly small DynamoDB cost. So limiting your app's a way to do it. And limiting your app kind of is useful for legacy applications as well. When you've got that wonky database that you've got to use at the back, or you've got an API of something, the examples I've seen of this is particularly in the like booking holiday industry. There's always like third-party applications that are rate limited, where you go and book hotel rooms from a hotel provider, or you're booking flights from an airline. You're always rate limited on it. Now you've got this amazing capacity at the front end using your serverless architecture, but you might overwhelm the back end. So you've got to start thinking about how you limit these things. Databases, third-party APIs, you've got to think about concurrency limits on them. So we have a concurrency metric built into Lambda, and it used to be a per account concurrency of 1,000 per region. You can now split that up per function. So you've got this pool of 1,000, but what you can do, you can say, I want to limit concurrency to particular legacy systems. So if I've got a function and its job is to talk to a third-party API, and I know that third-party API can only take 50 connections a second, I can then limit that function I've just written to 50 executions a second. That means I know I'm not going to overwhelm the third-party API at the other end. I've protected it. We can protect production services from other functions in the same account. So one of the things that I've seen here is people who've got functions that call other functions. You can end up with this really horrible cyclic runaway mess of your functions keep triggering each other, and how do you stop it? Well, you can actually turn the concurrency limit down to 0 on that particular function, and it'll kill it dead. So you can use this as a get-out-of-jail-free card almost. And we can also develop the runaway protection here, but develop limited billing as well. Limited billing means that you don't want a developer to be able to do a test to run 1,000 executions all at once for the next 6 hours every second, because that's going to give you a relatively big bill. You can put the dev account down and say, only let them run 10 executions per second every second for the next 6 hours. So you can kind of limit spend on your bill there as well. So you end up with something looking more like this with reserved concurrency limits. Function 1 here I've limited to only 200, function 2 to 300, which means I've got a much bigger pool for my unregulated, my unreserved execution for concurrency for my remaining 7 functions that I've got running. So you can use them as a mix. You don't have to give a value to each function. You can just pick ones that you want to limit to protect systems at the back end. Right, so how do you enable this? It's relatively simple. Anybody use the AWS CLI here? Anybody use it? Hey! You two can have stickers. I've got stickers at the end if anybody wants stickers as well, by the way. So it's really quite simple to switch it on. You give it the function name and tell it how many executions. You give it a value. Really easy to switch on. And if you want to then go and check what the actual limit is, if you do a get function, it'll bring back and give you a whole heap of information about that function, but it'll also tell you what the current concurrency level is on there. And switching it off, just as simple, going through there. So managing your concurrency and costs. Now, I talked about DynamoDB rather than using relational databases. And DynamoDB is a fully managed service. It performs at huge scale. We've got customers who use this. So Amazon Retail, for example, use this for delivering orders very quickly. Tinder, for your swiping left and right. It's all backed by DynamoDB. So it's fully enterprise ready and it's fully managed. And because it's fully managed and you've got no servers to think about, for all intents and purposes, it's serverless. You don't have to think about it. You say, database, go and do something. Now, I would have argued against that definition a year ago, because a year ago, if you wanted to do backups of DynamoDB, you needed to do horrendous things like run elastic MapReduce clusters and go and poll through all your tables and then recreate them and push them out into S3, and it was horrible. Backups is now built into DynamoDB, so you can just switch them on, and you can even do cross-region replication, so you can replicate everything into another region in AWS as well, relatively easy. So it really has matured as a product, and it's moved forward into that fully managed, fully serverless kind of database service for you. So a few examples of where DynamoDB is used at the moment. This is a weather application example pulled directly from our website. I stole the image from, hence it's got a horrible white background. I apologise. So S3 is hosting our main website. But when a user interacts with that website and clicks on something to get information, to do a post action, we send that via API gateway, we trigger a Lambda, we look up the data in the database, and then we return it to them for their geolocation. And this is a common type of very simple app use case. Other things in this. If you was going to create a website for listing products that people want to get rid of, think sites like FreeCycle, where people are posting adverts on. If you wrote those into DynamoDB, it'd be exactly the same kind of like architecture here. And this is actually incredibly cheap. Hosting a website in S3, I always recommend to put on things like CloudFront in front of that, the CDN product, because you can host directly from S3, but if you've got a very, very busy site, you can break it, and I've done that in the past, which is my claim to fame and why Amazon hired me, because I managed to break S3 in Europe. I'll tell you about that over a drink. But now with things like CloudFront, and now CloudFront's available, you can't really do it. So moving on there, you'd then have API gateway with your functions sat behind, and then you'd have your database at the back. Now, I've mentioned DynamoDB can scale up and down in the background dynamically. It's one of the features we offer now, so we can add in there, we can add extra shards as we need to go along, and then we can start consolidating that data and drop back down to save costs later. Lambdas, you're only paying per execution. API gateway is probably going to be your most expensive part of this. So it's a very cheap way to host a website. And most people, when they think about hosting websites in S3, think of static. It doesn't need to be. These components can make your website dynamic and interactive for very, very low cost. So another example here is social media analysis. So You could use Kinesis, which is our streaming database service. It's like a time-lapse window of incoming data. You can use that to ingest social media streams into Kinesis, and as new objects appear in the Kinesis stream, you can have that trigger a Lambda function. When that triggers a Lambda function, it might do something simple like just store it in DynamoDB for analysis later, or it might do something more complex like data enrichment. So you take that social media post, you get some extra metadata to go with it, and then you store the two bits of information together in DynamoDB. And then you can have a dashboard off that and show some analytics based on there. And there's obviously a load of other services you could strap in on there to use that as well. Another use case is with IoT. Because DynamoDB scales hugely and can ingest a lot of information, if you've got IoT devices, typically millions of devices, all trying to send information into DynamoDB, there's multiple ways of achieving this thing. This example uses SQS, but there's also an IoT gateway that can do the same thing. You can take this data, push it into DynamoDB, and then process that data at a later point. So there's lots of ways of taking advantage of that tier and that type of application that saves your effort and your complex management and heavy lifting of maintaining servers that run databases all the time. So I mentioned auto-scaling, automatically add and remove read-write capacity, read and write capacity there. I didn't finish these slides at 5 to midnight last night, honestly. I'll fix that spelling mistake later. And you can easily monitor usage. With CloudWatch, all the metrics from DynamoDB come into that, and you can monitor and see how busy and which functions are affecting read and writes on your database, so you can know where to control your concurrency. So in our case, and back to our diagram now, if we reduce costs, we could limit the amount of executions we handle in Lambda, which means we can have a smaller DynamoDB setup and save ourselves even more money if we wanted to. You'd obviously have to think about other problems that that's going to bring. If you do have an influx of a lot of users, how are you going to give them a nice end user experience to say, you're in a queue, please wait while we do things. The Ticketmaster style of things like, please wait, and you might be able to buy a ticket in a minute. So that type of problem you're going to give yourself. But you can control your costs with concurrency limits. That's the key to it. You can reduce the amount spend. You can protect back-end systems that maybe you can't scale. If you're using a relational database, for example, that's got a very expensive license attached to it and needs a particular type of processor, and if you move it onto a bigger instance even, you're going to get hit with another bill. I'm not going to name any companies who practice those kind of selling. There's a few knowing smiles happening around the room here. If you've got a system like that where you can't easily scale that database, concurrency limits will come to your rescue. And you can still interface with that database. You can still interface with that data you've maybe invested in over years and years and years, but you can not knock that server over constantly by overwhelming it with incoming connections. So if I now drop into a summary of what I was trying to tell you there, 1,000 executions per region depending on what service you're using and whether it's stream-based and whether you're polling or not. You can increase those limits with a simple raise a support ticket and give them a reason why you want to do that. It's really simple and most people get it increased. Consider your concurrency limits with the other integrations. So if you're doing stuff from S3, consider the fact that S3 is only going to give you so many events per second anyway. So if you've got 20,000 users all uploading images to S3, you're not going to trigger 20,000 Lambda executions all in the same second if all those images land at exactly the same second. In reality, that's never going to happen because images are different sizes, people have got different speed connections, they'll get spread out naturally. But if everybody was on the same speed, no latency, same size file, all clicked at the same time, you're not going to get 20,000 Lambdas invoked at the same time. They're going to get queued and processed going along. So think about your unreserved versus reserved capacity limits, and you can use those to do things like protecting legacy applications, control your costs, or even disable a function. And I have only ever had use for this once, where I'd written something that went into a little cyclic loop, kept calling itself, and because I'd forgot to rename the function that it was supposed to be calling, so it kept hitting itself on API gateway, and it was just going to run forever. So concurrency limits, turned it down to 0 on that function, killed it, fixed the code, happy days. So consider doing things like that. So this is a URL for getting started with Lambda. It's got a really good section about scaling concurrency in there. I really recommend reading, so you get a good grounding and understanding of how to do these things and where you might hit bottlenecks, if any. Like I say, most people won't hit bottlenecks because the scale of this is so big anyway. Most of our use cases day to day won't hit this. I would say even some of the competitions I used to run for the Beeb and for Channel 4, it wouldn't hit most of these issues here. Yes, we'd have 5,000 entries into a competition within a minute, but that's easily achievable within the standard tier and the standard concurrency of Lambda. That's 5 seconds worth of processing within a minute, spread out over a minute. So you're never going to really get there. The thing I'd really have to think about is my database. Databases are always your next logical breakpoint. When you fix a front end by using a cool technology like this, you're going to break something else. So we need to fix that. So DynamoDB, highly recommended.